Good day, friends. Today I plan to read out an article from Quanta magazine. Undergraduate appends a 40-year-old data science conjecture. A young computer scientist and two colleagues show that the searches within data structures called hash tables can be much faster than previously deemed possible. The article is by Steve Nadish and is dated February 14, 2025. Today is February 15. Sometimes in the fall of 2021, Andrew Krapivine, an undergraduate at Rutgers University, encountered a paper that would change his life. At the time, Krapivine didn't give it much thought, but 2 years later, when he finally set aside time to go through the paper just for fun, as he put it, his efforts would lead to a rethinking of a widely used tool in computer science. The paper's title, Teeny Pointers, referred to arrow-like entities that can direct you to a piece of information or element in a computer's memory. Krapivin soon came up with a potential way to further miniaturize the pointers so that they consumed less memory. However, to achieve that, he needed a better way of organizing the data and the pointers would point to. He turned to a common approach for storing data known as a hash table, but in the midst of his tinkering, Krapivin realizes that he had invented a new kind of hash table, one that worked faster than expected, taking less time and fewer steps to find specific elements. Martin Farag Colton, a co-author of the Teeny Papers and the Krapivin's former professor at Rutgers, was initially skeptical of Krapivin's new design. Hash tables are among the most thoroughly studied data structures in all of computer science. The advance sounded too good to be true, but just to be sure, he asked a frequent collaborator and a Teeny Pointers co-author, William Kurzweil of Carnegie Mellon University, to check out his student's invention. Kurzweil has a different reaction. You didn't come up with a cool hash table, he remembers telling Krapivin. You were actually completely wiped out a 40-year-old conjecture. Together, Krapivin, now a graduate student at University of Cambridge, Farag Colton, now at New York University, and Kurzweil, they demonstrated in a January 2025 paper that his new hash table can indeed find elements faster than was considered possible. In so doing, they had disproved a conjecture long held to be true. It is an important paper, said Alex Conway of Cornell Tech in New York City. Hash tables are among the oldest data structures we have, and they are still one of the most efficient ways to store data, yet open questions remain about how they work. He said, this paper answers a couple of them in surprising ways. Hash tables has become, I know nothing of hash table. Hash tables have become ubiquitous in computing partly because of their simplicity and ease of use. They are designed to allow users to do exactly three things: query, search for an element, delete an element, or insert one into an empty slot. The first hash table date back to early 1950s, and the computer scientists have studied and used them ever since. Among other things, researchers wanted to figure out the speed limits of some of these operations. How fast, for example, could a search or insertion possibly be? The answer generally depends on the amount of time it takes to find an empty spot in the hash table. This in turn typically depends on how full the hash table is. Fullness can be described in terms of an overall percentage. This table is 50% full, that one is 90%, but researchers often deal with much fuller tables, so instead they may use a whole number denoted by X to specify how close the hash table is to 100% full. If X is 100, then the table is 99% full. If X is 1000, the table is 99.9% full. This measure of fullness offers a convenient way to evaluate how long it should take to perform actions like queries or insertions. Researchers have long known that for certain common hash tables, the expected time required to make the worst possible insertions, putting an item into, say, the last remaining open slot, is proportional to x. If your hash table is 99% full, Kuzma said, it makes sense that you would have to look at around 100 different positions to find a free slot. In a 1985 paper, the computer scientist Andrew Yao, who would go on to win the AM Turing Award, asserted that among hash tables with a specific set of properties, the best way to find an individual element or an empty spot is to go through the potential spots randomly, an approach known as uniform probing. He also stated that in the worst case scenario where you are searching for the last remaining open spot, you can never do better than X. For 40 years, most computer scientists assumed that Yao's conjecture was true. Krapivin was not held back by the conventional wisdom for the simple reason he was unaware of it. I did this without knowing about Yao's conjecture, he said. His explorations with teeny pointers led to a new kind of hash table, one that did not rely on uniform probing. And for this new hash table, the time required for worst case queries and insertions is proportional to log x squared, far faster than x. This result directly contradicted Yao's conjecture. Farah Colton and Kurzweil helped Krapivin showed that log x square is the optimal, unbeatable bound for the popular class of hash tables you had written about. This result is beautiful, beautiful in that it addresses and solves a classic problem, said Guy Belloc of Carnegie Mellon. It is not just they disproved Yao's conjecture, they also found the best possible answer to this question, said Sefar Asadi of the University of Waterloo. We could have gone another 40 years before we knew the right answer. In addition to refuting Yao's conjecture, the new paper also contains what may be considered an even more astonishing result. It pertains to a related, though slightly different situation. In 1985, Yao looked not only at the worst case times for queries but also at the average time taken across all possible queries. He proved that hash tables with certain properties, including those that are labeled greedy, which means that the new element must be placed in the first available spot, could never achieve an average time better than log x. Farah, Colton, Krapivin and Kurzweil wanted to see if the same limit also applied to non-greedy hash tables. They showed that it did not by providing a counterexample. A non-greedy hash table with an average query time that's much better than log x. In fact, it doesn't depend on x at all. You get a number, Farah Colton said. Sometimes something that is just a constant and doesn't depend on how full the hash table is. The fact that you can achieve a constant average query time regardless of hash table's fullness was wholly unexpected even to the authors themselves. The team's result may not lead to any immediate applications, but that's not all that matters. Conway said, it is important to understand these kind of data structures better. You don't know when a result like this will unlock something that lets you do better in practice. Thank you.